Question 4. Here we have an infinitely long line charge. This goes off in both directions infinitely. This has a charge, a uniform charge per unit length, so it's a lambda. Okay. Well, lambda is equal to the amount of charge that we enclose over a length. It lies a distance d from this point O, the origin. Okay, so it's this distance d away. Determine the electric flux through the surface of a sphere with radius r, centered at O, that results from this line charge. So there's two options. We can make our sphere be smaller than d, so that's the first option, A, what happens when r is less than d. Or we could make our sphere very large, okay, and enclose, or be past d, and enclose some of the charge inside. Okay, so for the first part, for r less than d, we would look at Gauss's law, we would look at flux is equal to integral E dot dA, which would be equal to the Q enclosed over epsilon naught. Well, the amount of flux that would be through this sphere, there's no charge that is enclosed. The line is the only thing that has a charge on it. This sphere is not big enough to actually enclose any of that line, so the Q enclosed is 0. 0 over epsilon naught gives us 0 for flux. So for r less than d, our flux is 0. For the second part, it gets a little bit trickier. What happens when r is greater than d? Okay, then some of this sphere is going to enclose some of that line. Okay, so we can think of this distance d away. Let's say we've made our sphere rather large. Okay, something like that. Okay, now our distance r is larger than d. Okay, we go back to our equation for Gauss's law, and I want to see how much charge did we enclose. Okay, well, the amount of charge enclosed depends on how big we get our circle. It depends on the length that is enclosed. Okay, so if we enclose, if this is total length, let's call it L, that we enclose on here, okay, then the amount that we've enclosed would be lambda times L. So we would have flux is equal to lambda times L over epsilon naught. But what's L? That's the hard part on this. It didn't tell us anywhere in here was there an L involved. We made up L. So we can't leave L inside of this equation. We need to figure out what L is. Okay. Well, there's a couple of things. Okay, I can kind of find out into here. If the total length is L, then that means that this length here is 1/2 L. Right? This length will be 1/2 L. This is the other 1/2 L, because this circle will expand out uniformly as I get r larger and larger, and that'll always be 1/2 of the L, of the total length. Okay? So how am I going to find out 1/2 L? Okay. Well, this is just a right-hand triangle. So we should be able to go ahead and use Pythagorean's theorem of r squared, a hypotenuse, would be equal to the two sides, which is d squared, plus 1/2 L squared. That's the other side of the triangle. 1/2 L, d, and r. I want to solve for L here. R was given in the problem. Okay? D was given in the problem. So those are all numbers I can use. L's the one I got to take care of. So let's solve out for L. First, I need to move that d over to the other side, and then I bring in my square. So I'm going to have r squared minus d squared is equal to 1/4 L squared. Okay. Multiply this side by 4. Okay, to get rid of this one. and then take a square root on both sides to get rid of the square on the L. You should end up with L being square root of 4 multiplied by r squared minus d squared. Well, square root of 4, that one's easy enough. We can pull that out of the integral, or out of the square root, and we'll have that L is simply equal to 2 square root r squared minus d squared. Take this, and we'll plug it back into here. Okay. To do that, we'll get our flux would then be equal to lambda from up top. We still have that, and we have a 2 from over here, so we'll have 2 lambda square root r squared plus d squared. All of this over epsilon naught. Flux again, Newton meter squared per Coulomb. And that's how we get the answer up here.